Alright, this example we have a cube that's going to slide on a hemisphere. And let's start with our energy diagrams first. So we'll identify we have a change in height. So that means we're going to include gravitational potential energy. We have an object, so we're going to include kinetic energy. And we're not told anything about friction, so first we'll assume frictionless. Actually, no, we are told something. I take that back. We're told that it only reaches a height of 2/3 r, so we do have friction. And so we'll have energy dissipated or work by friction. Alright, so for A, all the energy is stored as gravitational potential energy because we're not told that A is launched. If we were told A was launched, it'd have gravitational and kinetic, but we're not told that, so we'll assume that it's from rest. At B, we're at the lowest possible position, so all of the energy now is stored as kinetic. And then at C, we're back at its maximum height again, but it's not the same height because some of the energy now is stored as dissipated. So we have gravitational again, but we have some energy stored as dissipated. In this case, the question could be, calculate the coefficient of friction. And let's see, that would probably work. Anyway, if that was the question, we would be interested in diagram A and diagram C. So that would tell us that we have gravitational potential energy is equal to gravitational potential energy after, so sub-zero, plus energy dissipated. So we have mgh0 is equal to mgh plus force of friction times distance d. Now here the challenge would be not finding distance d, right, because you could figure out what, it's a circular path and you could figure out what the distance traveled is. The challenge here, and then you'd also be able to find the height, that's no big deal either. The challenge here would be the fact that the normal force is constantly changing. So you'd end up writing an equation for force of friction based on your location. And that could prove to be a little bit challenging. Because remember, this one would be force normal times mu. And so what you would need is an equation that describes basically the radial direction depending on where you are. And that's more complicated than I wanted to look at right now. So let's just say that you would have that as your starting equation. That would be your energy equation. And we'll leave it at that for right now.